Okay, so we're starting off with our just kind of our toy artificial neural network. Okay, where we have two x inputs. We have x1, x2, and we have the y that we're trying to predict. And right now our predictions are, our input values are this, and the values that we have observed are this. Okay, and we want to create some kind of system that takes our two x inputs and we have a hidden layer, and then we have our output. Okay, and so what's going to go in is our data values. They get multiplied by weights. Okay, so we have the W1 matrix where there are 6 weights, okay, because we have 2 x values. So our W matrix is going to be 2 by 3. Just make sure I'm getting this correct in here. Okay, yeah. So 2 by 3. This is going to be W1, and then W2 is 3 inputs, 3 rows, and it's going to output to a single value, right? So this is going to be W2, and then this is W21, W22, and W23. And over here we got W1, 1, 1, W1, 2, 1, etc., etc. Okay, so these are the weight matrices, and basically, so our x will come in. Our x matrix is currently 3 by 2. We're going to have 3, 5, 5, 1, 10, and 2. And we're going to multiply this by our W matrix. Okay. This is our W1 matrix. And so the output here, what is our output going to be? What's our dimensions? 3 by 3, right? Okay, and we're going to call this matrix A. Okay, these are just x's multiplied by our w's. Actually, not really. It's just xw, not a dot product x. Okay. And then what we're going to do is we're going to take each of these values, and we're going to put them into our sigmoid function, right? So we're going to apply sigmoid function so that now we have f of a, and this is going to still be a 3 by 3 matrix, and this we will call Z. Oh, I'm sorry. Did I get my A's and Z's mixed up? Hang on, let me just go back. I might have mixed up the letters A and Z. Oh yeah, okay, I apologize. So after multiplying X and W together, that's going to be Z, and then after we apply the sigmoid function to Z, that's going to output our matrix A. So I apologize. Okay. Okay. So we're at this point, and that's so we're going to have basically we have 3 values because we have 3 inputs of X. So we have three values here that are going to be output, 3 values and 3 values. So we have a total of 9 values that are going to get multiplied by this matrix to produce our input for here. Okay, so let's just keep going here. Okay, so just kind of sliding this up. So we're going to take the this matrix, our 3 by 3 A matrix, and we're going to multiply it by our 3 by 1 the W2 matrix. Okay, and so the output here is going to be Z3, and this is going to be a 3 by 1 matrix. Okay, and then we apply our sigmoid function to this. Okay, so here each row represents an observation, right? Okay, and then and we apply the sigmoid function onto this, and this is going to produce our y hats. Okay, so this is a 3 by 1 matrix. Okay, and so now we can compare our y's to our y hats. Okay, and we can compute the cost. Okay, and the cost function, we've decided to go with y minus y hat squared. Okay, but we're going to just apply a constant of 1/2 to so that when we take derivatives, it goes away, and then we're going to just add up basically the squares of our residuals here. Okay, but multiplied by a constant of 1/2. Is this okay? And so if we were to basically ask how did we get to y hat, okay, so to get y hat is equal to x times w1, where a function is applied to that, our sigmoid function is applied to that, and we multiply this by our second weight matrix, and then a function is applied to that result. And this is how we're getting our y hats. Is that okay? So we're taking our x, we're multiplying it by a w, we apply the sigmoid function to that, we take those results, we multiply it by our second weight matrix, and then we apply the sigmoid function to that. Okay, so here I'm just basically building up y hat as kind of a nesting of functions of x and w. Okay, but these are basically the steps that we can just kind of code up, and so we can take derivatives of this, okay, because essentially we want to use gradient descent to kind of optimize this cost function. So we want to minimize this, and so we're going to take the derivative of this cost function. Just okay, so just for notation, we've called our cost function j. Okay, so let's find the gradient. Derivative of j with respect to our weights. Okay, because this is what we are adjusting, right? So we have two weight matrices. We've got W1 and W2, okay? So W2 is a 3x1 matrix, okay? One row, one row for each each node in the hidden layer. Okay, and then W1 is a 2x3 matrix, okay? So one row for each x variable. Okay, so we're gonna try to find the gradient of j, okay, with respect to W2 first. Okay, so this is going to be dj dW2. Okay. Well, I guess before I go on, I just want to make sure we're feeling okay so far. Okay, so we've established how we're going to go from our x values and our weights to get to our y hats, and then now that we've expressed our we have our cost function, we can take the derivative or find the gradient of this. Okay, so our cost function is the sum of the difference between each y and our y hats squared. And we're going to take this with respect to the second weight matrix. Okay, and because derivatives of a sum are just the sum of the derivatives, I can pull the summation out. Okay. Okay. All right. So applying the power rule, okay, we're going to just get y minus y hat, and then applying the chain rule, we're going to have y hat dW2. Okay, the y's there is y hat is a function of our weights, so that's why the chain rule applies there. But y's are just constant; these are just coming from the data, so there's no chain rule to apply there. Okay. So we'll deal with the sum later here, okay? And oh, I'm sorry. So when I apply the chain rule, I have to pull out the negative there, okay? With respect to y hat, okay? And then so if I can, to get to what is the derivative of y hat with respect to W2, we're going to have to further split that out, okay, into y hat, because the y hat is a product of our z matrix, which is the inputs into our sigmoid function, right? So so this is going to be split up into the z matrix, and then we so this is the we apply the okay, so here we're going to have to find the derivative of the sigmoid function. Okay, so the sigmoid function okay, so I want to take the derivative of this with respect to z, okay, so it's going to end up being e to the negative z over 1 plus e to the negative z squared. Okay, so this I can just kind of say this is our that's a e to the negative z. I should make this clear. Okay, so that's this is what's going to go in here. So dy hat with respect to z is going to be f prime of rz. Okay, so plugging that in, we have and then we finally have the z's with respect to our weight matrix. Okay. Okay. So if we flip back, the z's. If we think about what z3 is equal to, what is z3 equal to? Okay, this is our z3 matrix. This is just the A matrix multiplied by the W matrix, right? So if I want to know what is the derivative of z with respect to W, that's just going to be our A matrix, right? Does that make sense? Okay, so if we, so if we ask what is, what's our z matrix? Z is equal to A times W, the W2. So if I'm taking the derivative of Z3 with respect to W2, it's just going to be our A matrix. Okay, so this is effectively our A matrix. Okay, but we can't just multiply it straight up just because with matrix terms you got to make sure the dimensions line up, and so the the way we're going to get around that is we're going to transpose this, okay, to just make sure the alignment works out, and then that actually takes care of our summation. Okay, so just I guess I'll just write a summary over here. I'll just say recall Z3 is equal to our A2 matrix times our W2. So derivative of Z3 with respect to W2 is just our A2 matrix. Okay, so plugging this all in, we're going to have this is what we're going for, is going to be our A matrix. It's going to be our A2 matrix transposed times minus times y minus y hat multiplied by that. Okay, so this is we basically have an equation to get our gradient with respect to the first W matrix. This is okay? This is all from video 4 in the backpropagation video. Okay, so if you can review these notes, you can also watch the video to kind of just make sure you understand how this works. The nice thing is that if you have a simple what do you call it? Simple neural network where you just have one hidden layer. The fact that this is in matrix notation takes care of a bunch of dimensionality. Okay, so our particular example has 3 hidden nodes, but if you expanded that to 10 hidden nodes or 100, whatever, this will take care of that. Okay, you don't have to the process. If you're using the same cost function, the derivative still works out the same. So this is kind of nice. All right, so it's good to have a understanding of this for a pretty standard like this quadratic cost function. We've got that. Okay, so the other part is getting the gradient with respect to W1. Let's see, it's 2:30. I feel like we're gonna run out of time here if I work through all the math. So I'm gonna just kind of jump to the answer here, okay? And but I guess I can paste up kind of the step-by-steps. And I think the video, he works through finding the derivative very quickly in the video, but I think he does a very good job of explaining it. Okay, so what we end up getting when you take the derivative of the cost function with respect to the first weight matrix, you end up getting it takes into account the x data, okay, times this part from the other derivative multiplied by our second weight matrix transpose times the we have this okay, times the the derivative of the sigmoid function applied to the values being plugged in there. Okay. Okay, so I'll post notes. because I want to go into getting this all programmed into R. Okay, is this all right? So yeah, I kind of just waved my hands and said, here's our derivative, our gradient, with respect to the first weight matrix. Okay. Let's see. I'll also post these notes up. We'll clear our workspace. Okay, so I'm going to put in our data x. Okay, so this all this does is it just inserts the data into R here, and so we can see, you know, our x is just a 3x2 matrix. Our y is a 3x1 matrix. So this is pretty straightforward. Okay. We want to put these on even scales, basically from 0 to 1. So we're going to divide x by the max of each column. Okay, so if I go back and ask what x is, and I'm using capital X to indicate our scale data, this is what we have. And then if we ask what our scaled y is, it just basically puts our test scores into percentages or proportions here. Okay. So x goes on a scale from 0 to 1. Y also goes on a scale from 0 to 1. Okay. We're going to put this in. Our input layer size is 2. Okay. We've got 2x variables. The y is just a single value. That's our output layer. And our hidden layer size is 3. Okay, we've got 3 hidden nodes. Okay, so we're going to build our W1 matrix, okay, which currently I've just plugged in the values 1. Okay, so that's our 2x3 matrix of first our weights. Okay, and then we can show how we're going to get the Z matrix, which is just the product of X and W. And then here I've written some code to calculate the sigmoid. Okay, so we're just going to say, hey, if you input some kind of value z, do 1 over 1 plus the negative exponent of that thing. Okay, so you know we can just kind of test this out and just make sure the sigmoid function is working. So I'm going to create a sequence from -6 to 6 and plot that, and indeed this is what the sigmoid function looks like. Okay, so we can apply the so you know we can take a look at our Z matrix here. What's the dimensions of our Z2 matrix? It's the product of our X, which is 3x2, and our W matrix, which is 2x3. So Z is a 3x3 matrix, right? And this is just basically the product of, here it just says add everything up evenly, 1, 1, 1 with our X matrices. So it's not that exciting at this point. Basically we've just added these two together and these two together, and that's what we have here, and everything is applied equally, and we can apply the sigmoid function to that, and so now our A2 matrix is on the scale from 0 to 1. Okay, so whatever Z was, Z could be any value, and A2 basically takes that and turns it into values from 0 to 1. Okay, and then we're going to multiply our A2 matrix by the second weight matrix, W2, and we multiply that together by to get our Z3 matrix. Okay, so right now this is what our Z3 matrix is. We have one at this point. It's we've got one for each value there, and then we apply the sigmoid function to that, and this is our y hats. Okay, so we got one for each observation. So these are our predictions based on, if all of our weights were 1, okay, for weight 1 and weight 2, these are the predictions based on the input values we gave it, okay? Basically, we're saying, if we looked at our original data here, okay, we've got 3, 5, 5, 1, 10, 2. So currently it's just, we're applying weights of 1 to everything. So basically we're saying effectively each of these things are equally important, and this is how we're making our predictions. So effectively we're just plugging in 8, 6, and 12, and we're using that to make predictions which are not very good. If we compare our y to the actual values, we can see this is no good. Okay, so we're gonna we create a cost function. Okay, which it just says take each of your values of y, subtract off y hat, square that difference, add them up, and give me half of that. And so we can apply the cost function to our current values of y and y hat, and it says currently your cost function is 0.01532. 8. Okay, and we want to minimize this. Okay, and so to do this, we're going to use gradient descent, and we did all of the work of figuring out the values of the gradients. Okay, so we've got our gradient for dj dw2, and we got our gradient for dj dw1 here. Okay. So we're going to implement that. We've calculated a function for sigmoid prime, so we can calculate the derivative of this function when we plug in a certain value. Okay, and we can just kind of test this. All right, and so here's our sigmoid function, and then this is the derivative of that, which we see is has the highest value. This is the derivative right here, highest value right here, and then as it approaches the extremes, the derivative drops back down to pretty much 0 in those locations. Okay, looks almost like a normal distribution here. Okay. They're like cousins. Okay. All right. So, if you look at what the derivatives are, okay, the derivatives is our A2 matrix transposed times basically negative y minus y hat times sigmoid prime of the z matrix, okay, f prime of z. Okay, and so this is going to give us our derivative or gradient with respect to our W2 matrix, and this will give us our, and basically this is almost the same thing as before, except, basically I'm just reusing some code here. By calling this delta 3, I don't have to have the computer recalculate that. It's just getting plugged in back here, okay? Because if we look at the derivative, we see basically this bit of code or this bit of calculation, is repeated between the derivative with respect to W2 and the derivative with respect to W1. We see this part repeated between the two things. Okay, so we have this, all right, and these are the resulting gradients at our current location where all of my weights are 1, 1, 1, 1, 1. Okay, so these are the current gradients. And so we might ask, well, we can first test to see just if taking a step in the opposite direction of the gradient, right? Gradient descent is we take our current values and then we subtract off the gradient, right? Multiplied by our learning rate or whatever it is. We subtract off our gradient and we take a step in that direction. And so we can see if that indeed improves our cost. So our current cost is we're going to save as cost 1. This is the current cost between y and y hat. Well, what I can do is I can take a step in the direction of our gradient. So I'm just going to update our first weight matrix by subtracting off the gradient here, multiplied by a scalar. And then I'm going to update the second weight matrix by again subtracting off the gradient, multiplied by a scalar. So here now I have updated weight matrices, and I can check. So W1 used to just all be 1s. Now it's ever so slightly different. And W2 used to be just 1s, and now it's also a little bit different. So we've changed the weights that we're applying. We're going to use those new weights, W1 and W2, to calculate a new set of y hats. Okay, so our new predictions, are these better than what we had before? Well, we can calculate the cost of our new y hats, and we can compare the two costs. Okay, and so when all the weights were 1s, the cost function was 0.15. When all the weights have been adjusted, we see that our cost function indeed has decreased. So this is a good sign. Okay? So far, so good? Okay, so all we have to do is iteratively apply these steps, right? So every gradient descent, there's not a whole lot of checking you do. I mean, you can check for convergence, but basically you just take a step, calculate the gradient, take a step in that direction, calculate the gradient again, take a step in that direction, keep going, and you just keep doing that over and over and over again. Okay? You can check to see if the gradient turns out to 0, or you can just say, I'm going to just keep taking steps in the direction of the gradient, 10,000 times or something like that. See where I end up. Okay? The series of videos that I had you guys watch, and I do recommend, I think it's a very good series of videos, so I do recommend watching them again after today's lecture, after inspecting this code yourself, okay? Because, he uses Python, which is a great language. We're accustomed to using R, also a great language. Different strengths and weaknesses for both. So he recommends doing numeric gradient checking, and I don't think we have time to do this, but basically I've written the code to do that where we're going to manually perturb our weights and then see how much the cost function changes and divide by the amount of perturbation, which is basically how we calculate slope, right? The slope is the limit as the y's change with respect to x. So we can do numeric gradient checking. I mean, we can do that on Friday if we want. I kind of wanted to do something cooler, but we can do that. So we can just apply gradient descent here, okay? Now, so I'm going to just start off with some random values for our weight matrix, okay? W1 and W2 will just be some random weights of random uniform, okay? I'm going to keep track of the cost here as we go. We're going to say the scalar is this. And basically, I'm just doing the calculations, taking our current weights and finding, calculating the value of our y hats, and then we're going to find our the current cost, and we're going to store that in cost history. Okay, and then we do the part where we calculate the gradients. Okay, and we store those as dj dw2 and dj dw1. These are the gradients. And then we just subtract off the gradient from our weights, and this updates the weights that we're using. Okay, and then that's it. And we just we do that and then we do that again, and we do that again, and again, and again, and again, okay? And I'm gonna do this 10,000 times, okay? Because we're using matrix notation, the computer can handle this quickly, okay? If you tried to say like, oh, I've got 6 weights to calculate in this thing, so we're gonna do this one, and then we're gonna do this one, and then we're gonna do this one, it'll take a lot longer, okay? But because R has this, can handle matrices quite nicely, it can do all 6 together, or all 3 together in that other calculation, okay? So, so we'll try this, and it's just gonna run. Okay, it's done. All right, that's 10,000, okay? So we can see what our weight matrix looks like after 10,000 steps, okay? We got all sorts of crazy values here. And this is our second weight matrix, okay? We're still not quite sure what all of this means. All right, we can see how our predictions came out. What are the predictions based on these weights, okay? Well, it says basically our predictions here are 0.75, 0.82, 0.9296. Compare that to the values of y, and we can see, hey, these are pretty darn good, okay? And we can look at the cost. The cost is very small, and we can take a look at the cost history. All right. And so we can see, you know, initially the cost has dropped down quite a bit, okay? And it kind of became steady for a while. And a lot of times, sometimes this can happen in gradient descent. You end up in a land where it's very, very, very flat, okay? Maybe it's not completely flat, but very close to being flat. And so, depending on the algorithm, if you have something where it says like basically when the derivative turns to 0 you stop, sometimes the computer will look at this and say, hey, we're not improving, okay? So I'm going to stop here. And it might say you've reached convergence here, which might not be the truth, okay? And then, you know, just as it kept searching around, eventually it found a spot where you know, found some slot. I can show the log of our cost function, okay? And so even with the log, we see where the log emphasizes just dramatic changes, we can see there's still an area where it ended up being very close to being very flat, okay? And so a lot of times, you know, even in gradient descent, which is a pretty good method, but it's not perfect, it might think that it has converged somewhere where it has not, okay? You know, and your choice of the initial weight values can, you know, just imagine some kind of terrain, right? And you're basically just rolling a ball down the terrain to get to the minimum. Now, depending on where your initial parameters are or initial settings are, you might have put your ball in a very flat location to start with, okay? You know, there might be a lower area somewhere else, but where you put it, it could be quite flat, and so depending on where you start, your algorithm might have trouble, okay? Or, you know, it ends up going to another location. There's no guarantee that gradient descent is going to get you to the global minimum. It might get you to a local minimum that works well enough, but it's not guaranteed. Shoot, we're running out of time. Okay, well, I'm gonna post this up. This was kind of a manual implementation. I think the manual implementation helps you understand how gradient descent works. But the truth is we probably don't really do manual implementations of gradient descent, and we use kind of these very good implementations built into R. For example, there's a function called optim that employs different methods of optimization finding. One of them is BFGS, which is a gradient descent method that also takes into account the second derivative, the Hessian, which is quite good. So I've also written some code. I'll post this up. Please take a look at this code and study it. and you know, watch those videos again. Just make sure you understand what's happening in both that video and what's in this code that I've written, and we can review this again on Friday. So, all right, we'll see you guys in a couple days.